Hello, everyone. This is Ahmed Elthakeb from UC San Diego. Thanks very much for the invitation. So I'll present our work, Divide and Conquer, leveraging intermediate feature presentations for quantized training of neural networks. So the core idea of this work relies on two main insights. The first insight is the fact that in the context of neural networks, depth is a fundamental aspect of representation learning. And as it's commonly known, earlier layers learn low-level features, and as we move forward in the network, we learn higher and higher levels of abstractions. So, for example, we start by learning edges, then parts, all the way to complete object models by the end of the network. So, neural networks are really all about learning multiple levels of features. The second insight is the concept of knowledge distillation. And knowledge distillation is a generic approach which aims to reduce a large model down to a simpler or smaller model in a teacher-student paradigm. So combining these two insights, basically the hierarchical learning aspect of neural networks, which yields multiple intermediate features across the network, and by leveraging the concept of knowledge distillation, we define a new approach focusing on teaching the knowledge of such intermediate features to a corresponding quantized student. So, more specifically, given an input image, the typical training procedure for a neural network is through an end-to-end learning process. Here, instead, we propose to divide the pre-trained neural network into multiple subnetworks, and we leverage the intermediate feature presentations to feed into a newly defined regression losses at the interfaces of these subnetworks. So this way, DCQ provides a sectional multi-back propagation algorithm that leverages multiple instances of knowledge distillation and intermediate feature representations to teach a quantized student through a divide and conquer strategy. Here is the training procedure. So given a pre-trained full precision network, we split the pre-trained full precision network into M sections. For each section, we construct a subnetwork containing all the sections preceding and including the current section, as you can see. And for each subnetwork, so you can think of each of these subnetwork as independent training task. Now, for each of these subnetworks, we quantized all layers in the current section with the desired bit widths and set their weight parameters as trainable. So Q here refers to the weights being quantized, and T refers to the weights being trainable. Similarly here, the H refers to high precision weights from the pre-trained model, and F refers to freezed, means we don't train them. So we quantize all layers in the current section with the desired bit width and set their weight parameters as trainable. And we freeze the parameters of all the preceding or the remaining layers in the preceding sections. And then we perform sectional pack propagation for each subnetwork. Finally, we merge the quantized sections from each subnetwork training task to form the fully quantized student network. This algorithm outlines the step-by-step procedure for DCQ, putting together all the steps described in the previous slide. So in high level, we have a split phase followed by a merge phase. Looking into some experimental results, here we compare plain DoReFa versus DoReFa plus DCQ for binary and ternary quantization. Experiments on various benchmarks show that on average, incorporating DCQ improves the performance of plain DoReFa by around 21.6% and 9.3% for binary and ternary quantization, respectively. Additionally, we show that incorporating DCQ to existing quantized training methods leads to improved accuracies as compared to previously reported by multiple state-of-the-art quantized training methods. As such, this shows that DCQ acts as an auxiliary approach to boost performance of existing training techniques by applying whatever the underlying training technique or method, but in a stage-wise fashion, with defining a regression loss per stage. Now, in terms of ablation, we look at some of the we look at the loss analysis for DCQ. So as we mentioned, DCQ is basically divides is all DCQ divides the original classification problem into multiple regression subproblems by matching the intermediate feature maps. So when it comes to regression, there are multiple loss formulations that can be utilized. Here we examine three of the most commonly used regression loss formulations, namely the mean square error, mean absolute error, and Huber loss, which is a sort of a combination of both MSE and MAE. So this figure shows loss visualization while matching the intermediate feature maps. The first row shows the loss before using DCQ training, while the second shows after DCQ. Each column is for a different loss formulation. So the figure shows that first, the loss, or basically the amount of redness, is significantly decreased after incorporating DCQ as a result of regressing the quantized intermediate feature maps directly to the full precision counterpart. We also observe that this behavior is consistent across the different regression losses. However, based on our experimentation, the mean square error seems to be the most effective during the intermediate learning process. Here we show the actual feature maps before and after DCQ. And as we can see, the feature maps after DCQ almost match the full precision counterpart. And this primarily, again, is a result of directly regressing the feature maps to the full precision counterparts, which is the reference in this case. On another side, from implementation point of view, one more advantage of DCQ is that it enables parallelization towards training quantized networks. So since DCQ applies knowledge distillation through sectioning, it enables training each section of the sub networks independently and in isolation to deliver a quantized counterpart for the teacher, which can occur in parallel. In terms of memory requirements or overhead, with simple analysis compared to the conventional end-to-end training, DCQ only needs an extra set of weights divided across the training nodes, which is the same as any other conventional knowledge distillation approach. Nevertheless, DCQ does not impose any extra memory requirements on the activations. We also conducted some theoretical analysis, and here we briefly present a couple of these theoretical results. So one issue that arises as a result of the strategy of splitting into sections and training each section separately is the accumulation of error residuals through sections, which may impact the overall performance of the proposed technique. Here we theoretically drive an upper bound on the total accumulated error across the resulting subnetworks after splitting using a chaining argument and utilizing Lipschitz continuity. Theoretically, we show that even though there is a non-zero error after each section or subnetwork, when you chain the errors together, you can still bound the error and bound the overall misclassification probability. The theory is built on a chaining argument where you bound the error from layer, say, k-1, and that bound feeds into bounding the error at layer k. For more details, please refer to the paper. In conclusion, we developed DCQ, sectional multi-pack propagation algorithm that leverages multiple instances of knowledge distillation and intermediate feature representations to teach a quantized student through divide and conquer. DCQ achieves significantly higher accuracy compared to the state-of-the-art quantization methods by exploring a new sectional approach towards knowledge distillation. Finally, divide and conquer is a very basic and universal engineering principle that is commonly and widely applied across a variety of systems. DCQ here is a procedure that extends such effective concept or principle to the training of quantized neural networks. Thanks very much for your attention.